Hello everyone, welcome back to the series of NMR spectroscopy. In the previous video, we discussed something very important, which is impurities and residual solvent peaks in NMR. And I hope now, whenever you look at a spectrum, you are able to identify and ignore those extra signals. So now the real question is, what do we do next? All right, let's move forward. Today we are going to talk about one of the most powerful technique in organic chemistry, which is NMR spectroscopy. So NMR is one of the most common and comprehensive tool. It is an absolute technique for determining the structure of organic molecule. Now, in a broader sense, it works just like other spectroscopic techniques. Molecule interact with energy, they move into different energy state, and we analyze those differences to get structural information. But now over here the interesting part is NMR give us far more detailed information compared to techniques like IR spectroscopy and mass spectroscopy. Mind it, far more detailed information. Now, don't worry, in this video, we are not going into the complicated physics behind NMR. Instead, we will focus on something much more practical. So, in the previous video, we learned what we should not do. So now, when you see an NMR spectrum, what exactly should you look for? How do you start analyzing it? So, let's make it simple. When you look at a proton 1H NMR spectrum, there are few key things that give you almost all the structure information you need. And in this video, we are going to break it down into four main pieces of information. Once you understand these four, reading an NMR spectrum becomes much easier and systematic. So let's get started. The first thing is the functional group that are present in the molecule. May it be acid, may it be aldehyde, may it be amine, may it be ketone, may it be anhydride. So this is determined based on the position, which is generally we measure in ppm of the signal of spectrum. Most often the scale goes from 0 to 12 ppm. The second thing is the number of protons represented by each signal. This measured by the integration, which is surface area under each signal peaks. The third thing is the number of different type of protons in a molecule. This is determined by the number of NMR signal. Only non-equivalent protons give different signals. So chemically, equivalent proton give one NMR signal regardless of their number. And lastly, the fourth thing, the spin-spin splitting tells how many protons are connected to the neighboring carbon. This is determined by the number of peaks, means signal multiplicity, within the signal based on n+1 rule, n being the number of neighboring proton. So now that we understand what to look for in general, so let's start with the first and most important parameter, which is chemical shift. This is exactly what you see on the x-axis of the NMR spectrum, which is easily visible in the figure, which is mentioned over here. And you should know, what does it tell us? It tells us the energy value at which a particular proton absorbs radiation and give rise to a peak. Now, this might be sounds like a bit theoretical, but let's simplify it. Just like in IR spectroscopy, different functional groups absorb at different energy, right? The same idea applies here. Different type of protons, depending on their chemical environment, appear at different position on this x-axis. And that's exactly what help us identify functional group. So in the figure, you can see different type of functional group is mentioned. So the which I already told you, the scale is in between 0 to 12. The alkyl CH generally appears in between 0 to 2. Similarly, if we talk about more electronegative elements like acid and aldehyde, acid will appear in between 10 to 12, and the aldehyde will appear in between 9 to 10. Also, if we talk about aromatic one, the aromatic generally comes in between 6.5 to 8. So while in case of alkenes, they generally appears in between 4 to 6. So if any halogen atom is attached to the carbon which is having hydrogen, so sometime this alkyl group will shift to downfields from 0 to 1 to it will shift towards 3 to 4. Similar thing happens in case of alkynes. While if a heteroatom is having hydrogen like hydroxy, amine, so they generally appears in between 1 to 5. But if this hydroxy and or amine are attached to a aromatic ring, this will generally moves towards downfield. So next figure you can see like how a alkyl signal will shift from upfield to downfield. Like over here, if it is as methyl, it will generally come in between 0.7 to 1.3. If two different alkyl are attached, then it will shift little bits toward downfield 1.2 to 1.4. If it is tertiary or quaternary, then it will move further ahead at 1.4 to 1.7. Similar thing applies to other groups also. If carbonyl group is present nearby methyl, then it will shift towards 2.1 to 2.5. The similar, if any ester is there, it will shift towards 2.1 to 2.6. While in case of nitrile, it will remain in between 2.1 to 3. While if any methyl group is present, like in case of toluene, the methyl group generally comes at in between 2.3 to 2.7. The similar thing, if we start attaching different electronegative elements to the methyl like bromine, chlorine, it will start moving further towards downfield because of the electronegative nature of all these halogens. The similar thing, if you talk about any aromatic ring, it generally appears in between 6.5 to 8. Similar thing to aldehyde or acid in between 9 to 10. So you should know how which is called as downfield, which is called as upfield. Downfield means high energy, so it will appear on the left side of the spectrum, means higher ppm. Upfield means lower energy, it will appear in the right side of the spectrum, means lower ppm. So in the figure you can see this is the downfield and this is the upfield, and how they appear. If a particular proton is deshielded because of electronegative or any other attachment, it will move towards downfield. If it is shielded, then it will move towards upfield. So if the signal goes towards downfield, it will generally have higher frequency, and if it will go towards upfield, it will have lower frequency. So this is for this video. We will move ahead and discuss other thing in our next video. So stay tuned. Thank you.